Hi, hello, good morning my dear students. Today we are going to discuss the very important concept in chemical kinetics, that is integrated rate equation for zero order reaction. What is this? It's a very theoretical calculation part. Here it's not possible to determine the order of the reaction based on instantaneous rate of reaction or based on only the differential expression, because the integration rate of reaction is going to indicate that we are calculating the rate of the reaction for some duration of the time, means integration from one value to another value. In that duration it's possible to calculate the rate of reaction. That's why we are deriving integrated rate equation. This equation to calculate the rate of the reaction. Here to calculate the rate of the reaction we are having integrated rate equation for different order of the reaction. So order of the reaction is nothing but it is the power of concentration of the reactant, the sum of power of the concentration of reactant. Here if the order is 1 we are having different equation, and for the order of 2 we are having different. Same thing for the different order of the reaction we are having the different integrated rate equation. In the second PUC syllabus we are having only two kinds of the order of reaction. One is zero order reaction, another one is first order reaction. So here first we will begin with the derivation of integrated rate equation for zero order reaction. You should keep in your mind that here integrated rate equation, it is a derivation to calculate the rate expression or rate of the reaction using the formula of integrated. It's only for zero order reaction. For first order we are having different equation. So here we are deriving the equation for zero order reaction, the equation of integrated rate equation. So we will begin the first one. So it will be asked for 3 marks. Derive the integrated rate equation for zero order reaction. And one thing, particularly for this video, you are not supposed to be write by, no need of writing or making the notes by using the video, because I am going to send you the PDF files or the image of the notes. So based on that you can write down the notes. Is it clear? Okay, we will begin the first one. So look here, to calculate or derive the integrated rate equation for zero order reaction, first we know that what is zero order reaction. Zero order reaction is power of the concentration of the reactant should be zero. Here consider the general reaction. Consider a reaction for here R is going to form a P, means reactant is converted as product. If the zero order reaction, we know that for zero order reaction, so zero order reaction is nothing but we are writing that rate of the reaction, where rate is equal to K is the rate constant, concentration of the R, the power of concentration of reactant should be zero. If it is the power of concentration of the reactant is zero, this indicates that order of the reaction is zero. If the power of concentration of the reactant is 1, order is 1. If it is 2, it is the second order. Here rate expression for this general reaction, rate is equal to K. K is the rate constant, where R is the concentration of reactant. I have written the number of reactant is taken as only R. On the power I have written is 0. This 0 indicates that for the zero order reaction, order is nothing but it is the sum of powers of concentration of reactant. Here R is having the power 0. This indicates the zero order reaction. But we know that rate of the reaction, rate can be written as minus dr divided by dt. This is general expression. I hope you remember, this is the instantaneous rate equation. Rate is nothing but, initially we were writing delta R divided by delta T. Now onwards we are writing the delta is nothing but dr divided by dt. Here dr is nothing but differentiation form of reactant and differentiation form of with respect to time. Means differentiating the concentration of reactant with respect to time. Minus sign indicates that decrease in the concentration of reactant. So it means rate can be written in the form of, with respect to reactant, it is minus dr by dt. So that rate expression we are writing in this equation. So what happens? Rate is equal to minus dr divided by dt is equal to k as it is, small k, concentration of the reactant, r is to 0. Is it okay? Look here, we know that I will write it for one more step. K as it is, r raised to 0. If something raised to 0, x raised to 0 is equal to 1. If anything base, if the power is 0, that value becomes 1. Therefore, r raised to 0 is nothing but it is 1. Therefore, k into 1. K into 1. So I am directly writing this as r raised to 0 is going to form as a value 1. Therefore, k into r raised to 0 becomes k. Rate is nothing but minus dr upon dt. Rate is equal to minus dr upon dt. By substituting this expression, rate becomes minus dr upon dt is equal to remaining is k. To this expression, we are rearranging this representation just to send the negative sign of dr to the right side, and we are transferring the dt which is present in the denominator. We are transferring this dt to the right side. Therefore, it becomes, I will write it here, on rearranging the equation, what happens? I am sending minus that side, so remaining is dr is equal to, if minus comes this side, it becomes minus k, and dt is coming to the right side. Therefore, minus k into dt. Here, minus dr is equal to minus k into dt on integration. Means we are applying the integration to the both side, reactant and product. Means left side and right side we are applying the integration. So we know that differentiation and integration are opposite to each other. So it is differentiation of reactant. Integration, this is the symbol of integration. Integration of dr is equal to minus k is a constant. Therefore, I will take the minus k as it is outside. Minus k dt, integration of dt. So here, integration and differentiation they will cancel each other. The remaining is only the r. R is equal to minus k. Integration of dt is t. Means integration of dx is x. Similarly, the integration of dt is t plus I, where I is the integrational constant. Why I am writing here I is, we are doing the integration. The integration constant is written as I, where I is integrational constant. It is I is the integrational constant. So to calculate I value, we are going to calculate the I value. Here, to calculate the I value, I am going to put, consider this is equation 1. Just put t is equal to 0 when the time is 0. Initially means when the reaction is not beginning. At that time we are calling the time is 0. When the reaction begins, then we are starting the time. First, second, third, 4, 5, 6, like that. If the time is 0 indicates that there is no still, the reaction is not forwarded. It means when the time is 0, then the concentration of reactant R becomes R0. Here, R is nothing but concentration of the reactant at that time t. When the reaction is taken place at some time, the R is here, this one. R0 is nothing but it is the initial, means there is no reaction is carried out. Initial moment, the concentration is fully maximum and product is 0. Means it is initial time. Therefore, when the reaction is not still beginning, it is in the beginning stage. At that time, R becomes R0. R is nothing but concentration of the reactant at some time t. R naught is nothing but it is the initial concentration at the beginning. Here square bracket is nothing but concentration of the reactant. We will put the value here. This, therefore, equation number 1 becomes look here, when we put R is equal to R naught, concentration of R becomes R naught is equal to minus K into T. T value is 0. T value is 0. Therefore, the whole terms becomes 0 plus I remains as it is. Therefore, I is equal to what? Concentration of R naught means I is equal to R naught. Take this as equation number 2. Just we will substitute the equation number 2 in equation number 1 because we are calculated the I value by keeping the T is equal to 0 and R is equal to R naught. Therefore, I becomes R naught. By substituting equation number 2 in equation number 1, we are going to get R is equal to, as it is, we have to take the R everywhere as a concentration of R. If it is not written, there is no problem. But in the final equation, we have to write concentration of R is equal to minus K into T. It is as it is, minus K into T plus I is equal to what? I is equal to R naught. Therefore, R naught, I is equal to R naught. Look here we have to calculate the integrated rate equation for zero order. Rate equation is nothing but we have to calculate the equation for rate constant. K we have to determine. Therefore, K is here this side. We are not calculating the time, we are calculating the K. Minus KT. K is in the form of negative, therefore I will take this minus KT to the left side and we will send concentration of R to the right. Therefore, this minus, if it comes to the left, it becomes plus, and this plus of R, when it moves to the right side, it will become minus. Therefore, I am taking this minus KT this side, it becomes plus KT is equal to, initially R naught is as it is. When we move the right R to the right side, it becomes plus is converted as minus R, concentration of R. Are you getting this one? And K into T, we need K, therefore K is equal to the relation between K and T, the function is into here, K into T. Therefore, when T is ascended to the right side, into becomes divided. Therefore, R naught minus R whole divided by T. This expression is called as integrated rate equation for zero order reaction. And you are not supposed to forget here, in this expression, K is nothing but rate constant. R naught is nothing but initial concentration of the reactant. R naught is nothing but initial concentration of the reactant. R is nothing but concentration of the reactant at a time T. Concentration of the reactant at a time T. And T is the time. Are you getting? So soon after writing this expression, you also write what is K, rate constant, initial concentration of the reactant, concentration of the reactant at time T, where T is the time. This expression is called as integrated rate equation. It's important for 3 marks. You have to write from beginning to here. So here we see the integrated rate equation for zero order reaction. These are the 2 examples for the zero order reaction. So here the example 1 is the thermal decomposition of ammonia in the presence of platinum. So ammonia we are converting the ammonia into nitrogen and hydrogen. Here ammonia is undergoing the decomposition in the presence of platinum which is in the pot. Therefore, that is why we are calling thermal decomposition. Thermal is nothing but on supplying the heat in the presence of platinum, ammonia undergo decomposition to form nitrogen and hydrogen. So this is the example for zero order reaction, means order of the reaction of this decomposition of ammonia is 0. Similarly, the thermal decomposition of, we are supplying the pot in the presence of gold, the hydrogen iodide undergo the decomposition to give hydrogen and iodine. Therefore, these 2 are the example for zero order reactions. So Now we calculated the integrated rate equation for zero order reaction. Now it is one more interrelated to the next sequence or continuous question part of the first one. So commonly they are asking for 3 marks, derive the integrated rate equation for zero order, and simultaneously the same question will be continued for next for 2 marks. This write or derive the relation between zero order reaction and its half-life. What is half-life? Half-life is nothing but it's a time sequence required to form the exactly half of the concentration. Means initially it is R naught, concentration of the reactant is R naught. When the time is half the time of the duration, when the concentration, initial concentration becomes exactly half, that time is called as half-life of the reaction. So it means the thing that initially we are having 1 gram of any compound, say that it is X. Initially we are having X gram of the, for example, think that 5 gram of any compound is there. The compound A is having initially 5 gram. When it is time is 0. When the time required to convert this compound, we are taking this as reactant. The time required to convert the 5 gram of the compound A, when it becomes exactly half. Half means half of the 5 gram is 2.5. The time required to form exactly half of the initial concentration. How much time it makes? It may take 1 time. Means initially it is 5 gram. At 0 it is 5 gram. It may take 1 second, 1 minute, half minute, or it may take the 1 hour, 2 hours, or it may take 1 day, 1 week. It may take. So how much time the reaction takes to form exactly half of the initial concentration? The time duration is needed to form exactly half of the initial concentration. If initially 5, the half of 2.5. If the initially is 10 gram, the time required to become 10 gram to reduce it for the half means exactly 5 gram. To make it as 5 gram, how much time is required? This is called as half-life of the reaction. Half-life time. This is called as half-life of the time. The definition is also important. I will send this in a PDF notes. You can write the notes from that. Are you getting my points? What is half-life is nothing but it's a time sequence or the time durations required to exactly reduce the initial concentration to the half of its concentration. That the time is called as half-life of the reaction. So here, to make it as a half-life and zero order interrelation between these two reactions, we will take the zero order reactions. So where concentration of R is equal to minus Kt plus R naught. Do you remember this one? By substituting equation number 2 into 1 in the last equation, we have calculated this equation. R is equal to minus Kt plus R naught. This is the in-between portion, in-between reaction in the zero order reaction. While deriving the zero order reaction, it is one of the reaction obtained in the middle. Therefore, R is equal to minus Kt plus R naught. So you just write, consider a zero order reaction. This is not the final expression of zero order reaction. It's in between we have taken because it will be the easiest method to calculate. If we have taken finally, we have to rearrange that equation to this equation. So it's better to take from this one. R is equal to minus Kt plus R naught. Here, to calculate half-life, for zero order reaction is, we are going to take here. So we will put T is equal to T half. T becomes T half, means T is the time, T half is nothing but half-life of the reaction. And when we take T is equal to T half, the concentration of R becomes half of the initial concentration. Are you getting my point? when the time is taken as exactly half life of the time, P is equal to T half. T half is nothing but half life of any of the reaction. Here half life is nothing but when the initial concentration is exactly reduced to the half of the concentration. Half of the concentration means here at the time T the concentration of the reactant is R. At the T naught means initial concentration we are taking as R naught. When the T is equal to half life is nothing but half of the initial concentration. Therefore, this is the condition to calculate the half-life of the reaction. To calculate the half-life of the reaction, we have to substitute T is equal to T half. At that condition, R becomes R naught by 2. Y means exactly half of the reaction. Half of the reaction is nothing but the initial concentration of the reactant should be reduced to exactly half. R naught divided by 2. R naught is the initial concentration divided by 2. This is nothing but R, means concentration of the reactant at half-life. Therefore, by substituting these two values in the equation number 1, you can take this as the equation number 1. Now, R is nothing but R naught divided by 2 is equal to minus K. T becomes T half plus R naught as it is. Now again I will take this minus KT to the left side and R naught by 2 to the right side. So what happens? Minus K T half minus becomes plus K into T half is equal to R naught as it is, concentration of the reactant at initially, and this plus R naught by 2 when it moves to the right side it becomes minus R naught divided by 2. Can you see here in the R naught nothing is there in the denominator. If nothing is there means it is understood that 1 will be there. Therefore K into T half is equal to, by taking the LCM, if nothing is there 1, taking the LCM 2 into 2. Therefore, by multiplying both of the side, 2 in the left side, 2 R naught divided by 2 minus R naught upon 2. Therefore, this expression becomes 2 R naught minus R naught is nothing but R naught divided by 2. Are you getting my point? Below it is by taking LCM is 2. 2 R naught minus R naught means 2 R naught minus 1 R naught. 2 minus 1 is 1. Therefore, 2 R naught minus R naught becomes R naught divided by 2. The remaining is K into T half. So we need the relation between the half-life of the zero order. This is the zero order expression. Half-life is nothing but T half. Therefore, we need a T half. We can send this K to the right side. T half is equal to R naught divided by 2. This 2 and K we are sending to the right side, therefore it becomes 2 into K, small k. This is the expression for relation or interrelating the zero order reaction and its half-life. Derive the relation between integrated rate equation for zero order reaction and half-life means we have to begin from this expression and we have to substitute the T is equal to T half and R is equal to half of the initial concentration R naught upon 2. And by substituting this expression and you have to make the equation by representing half of the reaction, that is T half is equal to R naught upon 2K. Can you see here half-life of the zero order reaction where T half is nothing but it is the half-life of the zero order reaction and R naught is nothing but it is the initial concentration. R naught is nothing but initial concentration and K is the rate constant. And they may ask you the half-life of the zero order reaction is directly proportional to the initial concentration. Is directly proportional to the initial concentration and it is inversely proportional to the rate constant, and it means Here, half-life of the zero order reaction is depends on initial concentration of the reactant and rate constant. The same we are calculating for here before we are calculating the zero order reaction. Similarly, next we are calculating the integrated rate equation for first order reaction, and to that first we are relating to the half-life of the reaction to zero order, first order reaction. This is the relation for zero order reaction and its half-life, and next in the video tomorrow we are discussing about the integrated rate equation for first order reaction and its half-life. In that half-life we are differentiate, we have to compare the half-life of zero order reaction and half-life of first order reaction. So that's why keep in your mind this half-life of zero order reaction is depends on the initial concentration and rate constant. And you see here half-life of zero order reaction is depends on the initial concentration of the reactant and rate constant. So based on this we will continue the next derivation on tomorrow. If you are having any doubts, please text me and I will soon send you the notes. Okay.